it's your lucky day. You have not one, but two comparison tests that can help you determine whether a series converges or diverges.
Just a quick fiction thing. So series is a sum of sequences.
A series is a sum of the terms.
So the general, what is it called? General.
Yeah.
The general term looks the same, but the sequence is in brackets. And it's just a list of numbers.
Okay.
The series summation symbol, the sum of the numbers in the list.
Okay, gotcha. Thank you.
Okay, so we're going to use a comparison test to determine whether a series that looks almost like a p-series, but is not a p-series, or a series that looks almost like a geometric series, but is not a geometric series. If it's near those, then we can use a comparison test to determine whether or not the series converges or not. Our first comparison test, I'm going to draw the picture first. Remember that I'm denoting my series to look like the heights of sticks whose height is given by the general term. So we're talking about positive term series only. So that the series from k is equal to 1 to infinity, AK, denote a positive term series. So geometrically, it looks something like this. But these count my Ks, and these are the heights of each AK. So maybe this is A1 right here. This might be A2. This might be A3, and so on. You need it to go to 0 to have any chance of convergence. So that's a picture of my series of AKs. And suppose that all of the terms in this series look almost like the terms of a series whose behavior I know. So here's the series in red whose behavior I know. And consider the positive term series from k is equal to 1 to infinity. Let me denote them CK. And let's make all of my CKs mimic the black lines there, but just a little bit taller. So all of my CK values for each K is bigger than the values of the AK values. Consider CK with CK, I'm going to put AK smaller than CK. AK smaller than CK. Suppose I know the series CK. It's one of my favorite ones. P series, geometric series. Suppose I know it and I know it converges. I have my series lying underneath a convergent series. So the sum of those red sticks right there, if I were to pile them up one on top of the other, would be finite. You see how that's going to mean that some of the little black sticks would have to be finite as well? If this is a bigger term than that, then my bigger terms add to something finite, then my smaller terms have to add to something finite. That's part one of the direct comparison test. If my series has terms that are smaller than the terms of a convergent series, then my series converges as well. So that's part one. Here's part two. We're testing part two, not three. We're testing my series of AKs. And again, let's make the series of AKs look like the black sticks. I'm going to draw some red sticks for my series for DK. Here's what the AKs look like, just as before. So on. Now I'm going to draw my DKs next to them, but smaller. So all of my AKs are bigger than the series of the DKs. And I know this series of the DKs diverges. So the ones that I've written in red are known series that look like the series that I'm testing. If the series I'm testing has terms that look like these but not exactly the same, and I know these series diverges. In other words, the sum of those red sticks becomes infinite, and my series has sticks longer than those, then the series I'm testing also becomes infinite. So if it looks like a divergent series and it has terms bigger than a divergent series, then my series will diverge. Okay. So the CK series is a convergent lookalike series. The DK series is a divergent lookalike series. It's going to look like one or the other. Can't look like both. What the first part says is smaller than convergent is convergent. The second one says, oops, I need to say that part, that the AKs are bigger than the DKs. So that says bigger than divergent is divergent. Smaller than convergent is convergent. Bigger than divergent is divergent. Yes, sir. Exactly. And then we find another comparison test. That's the problem with this comparison test. You have to know the sizes, and the sizes have to line up right. So this one says smaller than convergent is convergent. This says bigger than divergent is divergent. It's screwed up in any other way than the test can't be used. Smaller than convergent is convergent. Bigger than divergent is divergent. We construct a lookalike series. We do that first by throwing away terms from the AKs that really don't provide any information to us. We construct the series that I've written in red. Then we make a decision on the series that we construct. Is it convergent or is it divergent? Then we compare in size. And if the sizes line up just right, then we can use this test. So I've got a little bit of room right here. I'm going to do a little tiny example right in here. Let's test the series from k is equal to 1 to infinity of 1 over k cubed plus 5. plus 5, when k is large enough, doesn't do diddly. So when k is large enough, this behaves a lot like the series 1 over k cubed. Agree? 1 over k cubed is a series that has a name. It's a p series with a value of p equal to 3. Does 1 over k cubed converge or diverge?
Converge.
It converges. So this looks like a convergent p series. Now let's see how it compares in size. So I'm going to pick my lookalike series. As the sum from k is equal to 1 to infinity of 1 over k cubed. I know that this is a convergent p series. So now I'm going to compare my terms, my AKs, with my CKs. So here we go. I know k cubed plus 5 itself is bigger than k cubed because it's 5 more. So 1 over k cubed plus 5 has to be smaller than 1 over k cubed. In an inequality, when you flip both sides, you change the direction of the inequality symbol, right? Or think about cross multiplying, then the k cubed plus 5 would be the bigger. The bigger denominator makes the smaller fraction. And so my series has terms that are smaller in size than the terms of a convergent series. So my conclusion is smaller than convergent is convergent. Smaller than convergent is convergent. That's the direct comparison test. Sorry? For both cases. Smaller than convergent is convergent, bigger than divergent is divergent. That's the Reader's Digest version of the comparison, the direct comparison test. Smaller than convergent is convergent, bigger than divergent is divergent. And we're going to note the direct comparison test. Direct comparison test. Direct comparison test. One very similar. My next example is the series 1 over 2k minus 1. This would be real easy to integrate. Do the integral test in your head. What do you get when you integrate 1 over 2k minus 1? You get a logarithm, right? And so when you evaluate it for n going to infinity, your logarithm is going to go to infinity. The integral test can easily show you in 2 steps that this series diverges. Agree? So does the comparison test. This series looks like the series 1 over 2k. Right? So let me just make a note as I can. You can easily show This diverges with the integral test. But if we use a comparison test, if we use our direct comparison test, we would compare this to the series 1 over 2k, 1 over 2 times k, sorry. The 2 itself, that doesn't matter, but I'm going to leave it there. This is another p series. The constant doesn't change in front. You can always factor constants out. What kind of p series is this one? P is 1. P series when p is 1 or smaller diverges. Right? This is a divergent p series. So now we're going to compare the sizes of the general term. My general term has this in the denominator, which is just slightly smaller than the term that has this in the denominator. So when I do the reciprocals, the series that I'm testing has terms which are larger than the terms of a divergent series. And the second statement of the direct comparison test applies. Bigger than divergent is divergent. Make sure you tell me which part that it's bigger than a divergent series.
Okay.
The problem with the comparison test is you've got to have the sizes going in the correct direction. Or at least you got to at least know how the sizes compare. So for example, suppose I want to test this series. Well, I pick a comparison series that looks like it. The term in here that keeps this from being a p series right off the bat is that -5. Throw the -5 away and I've got my comparison series. So I'm going to compare it to series k over k cubed, which simplifies to 1 over k squared. 1 over k squared is a convergent p series. So I picked my lookalike series. It's a convergent p series. So I need to see if my series that I'm testing has terms that are smaller than this convergent p series terms. But when I look at my terms, k cubed -5 is a smaller number than k cubed. So 1 over k cubed -5 is a bigger number than 1 over k cubed. And now if I multiply both sides of that inequality by k, I see that my direction goes the wrong way to apply the direct comparison test. The terms in my series are bigger than convergent. And there's no part of the direct comparison test that says bigger than convergent is convergent. We don't give up. We can't use the direct comparison test. Because the size comparison is off. Sometimes it's even hard to compare the size, or it's a pain in the neck to compare sizes. So to the rescue is a new and improved comparison test called the limit comparison test. It gets clothes wider and teeth brighter than the direct comparison test. The limit comparison test involves comparing your lookalike series with your series in a limit. Okay, so to test positive term series for convergence, convergence or divergence. We'll say test for convergence is the same as testing for divergence. It could be one or the other. You still form the lookalike series. Let's call it BK this time. Whose convergence or divergence you know. Then you take a limit. Of the terms in the testing series with the terms in the BK series. If the sizes aren't right, but they still kind of follow each other, then they're both going to do the same thing if you get a finite limit. So if the limit of these is equal to L, and L is a positive finite number, that means that the numerator is behaving like the denominator, right? We have a ratio that is some number. So if you get a limit that's a positive finite number, they're following each other. So the AKs do what the BKs do. So let's go back to our example. I can't use a direct comparison test with k over k cubed minus 5, but I can do a limit comparison test with 1 over k squared. That over. We're going to do it right there. We're going to do the limit comparison test right here. So I'm going to do the limit comparison test. The series that I'm testing was k over k cubed minus 5. And my known series is the BK series, which was just K over K cubed, or 1 over K squared. Convergent P series. Let's take the limit of the AKs over the BKs. All right, so my AKs were K divided by K cubed minus 5. I look at my BKs in their simplified form, 1 over K squared. I can put that together as a single fraction by doing the flip and multiply step. When I flip and multiply, I get a K cubed on top and a K cubed minus 5 on the bottom. Is that something that you know the limit of? It's 1, right? In the limit comparison test, if you get any positive finite limit, both series do the same thing. Up here, we said that was a convergent P series. So my lookalike series was a convergent P series. That means my series converges. That's by the limit comparison test. The limit comparison test, we don't care which one's bigger or smaller. We just make a quick limit of the given series with the BKs, and they follow each other. If you get a positive finite limit, they follow each other in such a way that the AKs do what the BKs do. It doesn't converge to 1. That's just the limit of the ratio of the terms. The 1 says that they almost behave in a 1-to-1 manner with each other. Right? Limit comparison test, LCT. A lot of folks like it better because you don't have to worry about sizes. Just compare away. And it helps when you've got a bunch of terms and you can't really throw a lot of terms away. So take a look at the limit comparison test with here. And then keep in mind, we've got 2 endpoints we're going to talk about here in a second. What happens if the limit is 0? What happens if the limit is finite? I'm sorry, infinite. But I'm going to erase this for now and come back to them after another example. Well, you guys are working hard today. If it wasn't for you, I'd have quit a long time ago, but you guys are just pushing me. So I'm gonna keep going.
Just read through. Could you read it?
Say again?
How would you do K-cubed or K-cubed?
I'm doing just the limit by itself is 0. I don't want the limit by itself, I want with a comparison series.
Right, and then like that sum is equal to 1.
Oh, okay, because the powers are the same, right? The powers are the same, you take the ratio of the coefficients.
Oh, okay.
Bigger powers on the bottom, the limit is 0. The bigger powers on top, the limit is infinite. Okay, so here we go. Go. Another example. All right, I filter the series k squared plus 4k minus 2, all divided by 8k cubed plus 6 times the square root of k plus 5. And I claim that this is an ideal candidate for the limit comparison test because for the first thing, when I do the quick test for divergence, I do have a term. Oh, no. What does the test for divergence say to this? The limit of the kth term. It doesn't equal 0. The limit of the kth term is 1a. So I'm done. The series diverges. Woo. So let me change it. Let me make this a 4. So the k to the 4th, so the kth term does go to 0. Okay? So I do my test for divergence now, and this time the limit does go to 0. So it means try something else. Well, this is clearly not something I want to integrate, and it's not a p-series, and it's not a geometric series. So I'm going to make a series that throws away the insignificant terms. When I look at the numerator, the one that's having the greatest effect in the numerator is the one that has the higher power, right? I want to know what's happening in the long run when there's large k's. So the k squared is controlling the behavior of the numerator. The 8k to the 4th is controlling the behavior of the denominator. So I'm going to make my lookalike series to throw away all the lower powers of k. Okay, so we form a lookalike series. Throwing everything away on the top except for the k squared. Throw everything away on the bottom except for the 8k to the 4th.
I have a question.
Yes.
So in my head, I have a series of k squared.
Uh-huh. That makes it easier for me to do the limit, but you can throw the 8 away as well.
Oh.
But now I threw things away from the denominator and I threw things away from the numerator, so I can't tell if I made something bigger or smaller. And you know, I don't care because I've got that new and improved limit comparison test. Why waste time with details of the direct comparison test? So I'm going to go ahead and form the limit with my given series to my lookalike series. I'm going to do the limit comparison test. Take the limit as k goes to infinity of the general term of the tested series to the known series. First, you're going to tell me what my known series does. It's a convergent p series. Because the p is the 2, right? If I get a positive finite limit, both series are going to converge because my comparison series converges. So I take the limit. K goes to infinity, put my AK term on top. Put my BK on the bottom. And try to take that limit. So I know the next step is to flip my BK over and multiply. So when I multiply that through, I'm going to have my highest power of k on top to look like an 8k to the 4th, which is also the highest power of the k on the bottom. So what should the limit be?
1.
1. And had I thrown the 8 away, our limit would have been 1/8. So it doesn't matter whether I keep the 8 or not. If I get any positive finite limit, both series do the same. And so my conclusion is that our series that we're testing converges by the limit comparison test. Both follow each other. By limit comparison test. So let's look at the 0 and the infinity case of the limit comparison test. What happens if my limit is 0? What happens if my limit is infinity? Now, so remember, this is the one that we're testing. So we know what the B Ks do, we just don't know what the A Ks do. And we form this limit. What causes this limit to be 0? That's right, if the B Ks grow faster than the A Ks, or the B Ks are bigger than the A Ks, or say it this way, the A Ks are smaller than the B Ks. If that limit is 0 and the B Ks are known to converge, that means I've got A Ks smaller than a convergent B K. And then the A Ks will converge. So you need two things to happen. You need this limit to be 0 and our lookalike series converge. If the limit is 0 and our lookalike series converges, then our series converges. Because that's just a restatement of the statement in the direct comparison test that smaller than convergent is convergent. What causes that limit to become infinite? If the A Ks are bigger, right? So if the limit is infinite and the B Ks diverge, that's a restatement of the statement from the direct comparison test that bigger than divergent is divergent. I would say if this happens, if the limit is 0 and the B Ks converge, then I say the A Ks converge by the 0 infinity case of the limit comparison test. If this happens, I say the 0 infinity case of the limit comparison test. It is possible for this limit to be 0 and these guys to diverge, in which case we don't know anything. If the limit is 0 and the B Ks diverge, the test doesn't apply. If the limit is infinite and the B Ks converge, the test doesn't apply. We've got to have another test. So we look at all of our other tests. We don't have a great deal of other tests. We might try to integrate, we might try to, right? When you looked at the K cubed minus 5, we could possibly do some sort of partial fraction decomposition and try to integrate this. Comparison tests are like a quickie. But if it doesn't fit any of our comparison tests, we got to try something else. Okay? Comparison tests work when you have things that look like polynomials or things that are almost geometric. So let me see if I can find something that's almost geometric. I don't know. I don't know. Okay, I'll just make one up. What the heck? K times 3 to the K divided by 2 to the K plus K squared. It looks to me like the top grows bigger than the bottom. I wanted it to be more ambiguous than that. But I put some more terms in there so the bottom goes faster. Not this one. Is it obvious that the top grows faster than the bottom, or is it? Maybe not. You can think of that as a K squared plus 1 times 2 to the K. It's hard to tell. I mean, we could probably try to do a limit and try to do L'Hopital's rule. If you remember how to take the derivative of 3 to the K and 2 to the K. But you forgot, I remember. So I'm just going to assume that the limit goes to 0 because I don't want to take the limit. It looks like it would be kind of hard. What do you mean? Well, you don't know how to do L'Hopital's rule, and you can't convince me that the top is growing faster than the bottom. I can put more terms in the bottom if you want me to.
Or just leave that at that. Assume that's- All right, one second.
Yeah, I can't make the bottom bigger until you're not sure, really not sure which one's bigger. But if I want to do a comparison test, I would try to keep the most influential term on the numerator and the most influential term on the denominator, and then compare them. So what would your lookalike series be? I'm going to do either a direct comparison test or a limit comparison test. So I'm going to compare it to what? Okay, that's the good news on top. What are you going to take as a big boy on the bottom?
K squared times 2 to the K.
K squared times 3 times 2 to the K. 2 to the K. So that behaves like 1 over K times 3/2 to the K. Maybe? I don't know what that one does. But I can compare it to something. In my comparison test, I could do another comparison test. Oh, but I'm opening up a can of worms when I do that. I don't want to do that. So I don't want to do that. Yeah, that's bad.
Press the easy button, just erase the whole thing.
I want to erase the whole thing. I'll just erase
The whole thing.
that thing. We'll put a 3 here.
Oh, shit.
That'll make it easier for you. So I'm gonna do that. I'll be more careful on the test. I'm just making up examples here off the top of my head. I'm like dehydrated, exhausted. You guys are working me to the bone. What if you made a harder problem? Then I have to grade the harder problem. Because you're that way.
Don't worry. we're
You
not
just
gonna
be-
make a harder problem.
I am worried. I've seen it done. Then I'll stick the people from that class on you. Okay, if I make that a 3 to the K, it's still the most influential term on the bottom, right? But now my comparison series simplifies a little bit better to 1 over K. What do you know about that?
Divergence.
That's a divergent P series. This is called the harmonic series. P is 1. So putting that 3 to the K there was a good idea because it made the limit clearly go to 0. And now I'm comparing it to a divergence series. And do I know that my series is bigger than divergent? No, my series is much smaller, right? Because it's got more junk on the bottom. If you divide by more stuff, you make a smaller fraction, right? So my series is smaller than divergent, so the direct comparison test doesn't apply. Let's do the limit comparison test. So I've got all of that divided by that. So I'm going to go ahead and do the flip and multiply step right in my head. Right? Take all of this divided by that. So I flip that over and this simplifies. Limits k goes to infinity to multiplied by k squared, 3 to the k, 2 to the k, plus k squared, 3 to the k, plus 8k, plus 1,000. Right, so I did that flip and multiply step already. Can you tell what that limit is?
0.
Not really bigger on the bottom. The highest power, top and bottom, follows these guys. So in the long run, those two are the ones pulling in the same direction.
Yeah.
The ratio of their coefficients would be the limit. So it's 1. I get a positive finite limit, so both series do the same. The series we're comparing it to diverged. Our lookalike series diverged, so our series diverged. Whew. I'm quitting, you can't make me stay. Oh, and look, time's up.
Yeah.
Okay, so I think I put you some web work for this section on there. If not, I'm gonna run to my office and do it right now before you can get to your computer and see whether I did it or not. Maybe. But keep working, keep working, keep working, keep working. Questions for you fellas at home? Anybody still awake out there? Can I grade anything? My camera went out. Sorry, you'll have to check. I'll post the video and let me see if I can get my camera back on. Let me see if you can see it.
Professor Patton.
Yes?
What are your office hours?
Before and after class.
Oh, okay, okay.
Tuesdays and Thursdays I'm down all afternoon. I'll go to the left a little bit. Which way's the left? See if this is the left. Is that okay? Oops, no, it's gone. Is that the wrong left? Which left? This left? Okay. And then the other stuff is erased. All right, what you got? Where'd you get to? You're saying two times?
There's such a calm.
I'm so like happy that.
You want that?
I don't think so.
No, that was it. Then we put some infinities minus infinities in between.
Oh. Yeah, I thought that was.
That's your mind going goofy.
Yeah. But one thing that I noticed, like, it's like a teacher.
Uh-huh.
Yeah. It's kind of like, there's some limits. So, right. One pattern I noticed is that if PK is bigger than PK, like this was a term that we used back in the obviously it's called Bobo, bottom. So Bobo stands for bigger on bottom, where BK is for the AK, and then zero.
Okay.
Bigger on top, it's still from non like this.
Right. Right.
But nine could just be. Right. CC. Not where it's just network. I just remember the last one it's divided coefficients.
Right, so that must mean they're the same.
Yeah. So if AK was the same way.
That's right. That's right.
So I don't
But
know.
I have a hard time remembering all of our I have a hard time remembering that.
But I just kept doing slow.
But that's right.
You just do the one. And you're like, oh yeah, it just goes to this. Now it's like taking so much computer.
That was it. That's right. That's how folks will remember make those statements like that.
Also, I have one question because we're doing like this and adding like hatch charts, right?
Yep.
Will I ever reach a point where I'll do something like?
We do everything in real numbers.
Okay.
You have to take complex analysis in order to do all the calculus with complex numbers. So there is a such thing.
Yeah.
It's just not in.
I hope
calculus.
there's a such thing.
This
as
is
that.
real variable calculus. Everything is real value.
Lost.
That would be upper level math classes. See, in the complex plane, things go in circles, just like polar coordinates. So it's harder to take a limit.
Okay.
You've got to have things that circle in toward a spot of the complex plane, while they circle away from it. So you got to know a little bit more about the complex plane.
Right over my head.
Yeah, well, but just like the polar coordinates.
Okay.
So you have like the limit maybe as you go toward the origin, which is called the pole. So you're seeing what's the behavior of your complex function near the pole. Is it spinning toward it or spinning away from it? Spinning toward it, you're good. Spinning away from it, is it going somewhere in the complex plane? The complex plane behaves kind of like vectors. Kind of.
That's weird at times.
Yeah.
I swear I ask questions that are above my head and then I keep looking at these.
But the funny thing is that there's usually an answer to your question.